Imagine a busy kitchen where multiple chefs are trying to use the same shared pantry, or a digital bank where many transactions are happening simultaneously. Without a clear system, chaos would ensue, and your delicious meal or accurate bank balance would be at risk. In the world of programming, this challenge is elegantly solved using two fundamental approaches: atomic operations and locks. The core difference between atomic operations and locks lies in their granularity and the mechanism they employ to ensure thread safety. Atomic operations guarantee that a single memory access or data modification completes entirely without interruption, making it indivisible from the perspective of other threads. Locks, on the other hand, provide mutual exclusion for a larger block of code or a critical section, ensuring that only one thread can execute that section at any given time. Atomic operations are typically very low-level, often directly supported by the computer's hardware. They are designed for simple, single-value updates, like incrementing a counter or setting a Boolean flag. Because they are often implemented as a single hardware instruction, they avoid the overhead associated with operating system calls and context switching, making them incredibly fast and efficient for these specific tasks. Locks, such as mutexes or semaphores, are higher-level software constructs. They involve the operating system to manage access, putting threads to sleep and waking them up, which introduces greater overhead. Their power lies in protecting complex sequences of operations or entire data structures, where multiple steps must appear as a single, consistent unit. To put this into practice, you would typically opt for an atomic operation when you need to perform a simple, independent update on a primitive data type, such as updating a shared counter or flipping a status flag, and high performance is critical. If your task involves manipulating multiple related variables, accessing complex data structures, or requires several lines of code to maintain consistency, then a lock is the appropriate tool. Locks ensure that no other thread can observe or modify the data in an inconsistent intermediate state. Understanding these differences also opens the door to advanced concurrency patterns like lock-free and wait-free programming. These techniques often relying heavily on atomic operations to achieve high performance and avoid the potential for deadlocks or priority inversions that can sometimes arise with traditional locks. However, implementing these patterns effectively is complex and can introduce subtle bugs, such as the ABA problem, where a value changes from A to B and then back to A, making it seem unchanged to a simple atomic compare and swap operation. This highlights the precision required when working with low-level concurrency primitives. Ultimately, both atomic operations and locks are indispensable tools in a programmer's toolkit for building robust, thread-safe applications. Choosing between them hinges on the specific task at hand, the complexity of the shared data, the number of operations involved, and the performance requirements. By carefully selecting the right mechanism, you can ensure that your concurrent programs run smoothly, efficiently, and without unexpected data corruption.
If this helps you fix faster, like, subscribe, and keep debugging with us.